Good day, everyone. Thank you for joining our Technical Tuesdays webinar series. I can see that many people have already joined this session. Let's give another 1 to 2 minutes to arrive before we start. Hi, once again. I am Alan Ignacio, Senior Project Geologist here at Sequent based in Perth, and I've over 25 years experience with exploration and resource evaluation. My co-presenter is Putra Sadikin, an experienced geochemist and senior software analyst from IMDEX Limited. Putra, can you tell more about yourself?
Thanks, Alan. It's a pleasure to be here to presenting this webinar with you guys today. So I work in a product management team for the ioGAS software. I look after product support, training, and a bit of sales and research and development work for the software. My background is in geology. And today we'll be presenting a bit of a workflow between ioGAS and Leapfrog Geo, and I'm really excited to be here today. Thanks, Alan.
Thank you, Putra. So today's presentation is about linking lithology and geochemistry through the use of Leapfrog Geo and ioGAS. The purpose of this presentation is for us to appreciate the live link between Leapfrog Geo and ioGAS, as well as have the opportunity to analyze various multi-element data, which could provide hints to determine different rock types, alteration, and mineralization patterns that normally our naked eye couldn't immediately see. Just going to turn off my camera now before I proceed with the presentation. So we would like to outline a few housekeeping rules for the duration of the webinar. All participants will be muted for the duration of the webinar. Please use the chat window to ask any questions as we move through the presentation. Our team will endeavor to reply to all questions and requests during and after the webinar. You will receive a link to the recording of this webinar in a follow-up email. Also, let me introduce to you Catherine Gall, Senior Technical Lead at Sequent Australia. Catherine will be helping us to collate the questions as they come through during the session. So for today's webinar, we'll first give you an overview about our company. Then I'll be going through a series of PowerPoint slides on Sequent solutions, including Leapfrog Geo and ioGAS Link. We'll give you a bit of background about the data set that we used for multi-element analysis before moving into the Leapfrog Geo and ioGAS workflows, which I'm pretty sure all of you will find interesting and useful. And then we'll jump into the live demo on Leapfrog Geo and ioGAS workflows, and then end it with a summary. So about SEEQUENT. SEEQUENT is a global leader in the development of visual data science, software, and collaborative technologies. We turn complex data into geological understanding, provide timely insights, and give decision makers confidence that they need. Our SEEQUENT solutions harness information, extract value, bring meaning, and reduce risk. Our 3D modeling tools and technology are widely applied across industries and projects, including road and tunnel construction, groundwater detection and management, geothermal exploration. We also have something in resource evaluation and estimation, subterranean storage of spent nuclear fuel, and a whole lot more. So the SEEQUENT solution encompasses a range of software products applicable for the use across the volume mining chain. We have the GeoSoft suite of products and the Leapfrog suite of products, both for GIS mapping, geophysical, geochemical, geological, and resource modeling. And we also have the GeoSlope products that are designed for geotechnical engineering problems. I'm sure many of you are already familiar with some of these solutions. Models can be integrated using SEEQUENT Central for model management and collaboration. Today, we will be focusing on Leapfrog Geo, ioGAS, an IMDEX product, and the Leapfrog Geo ioGAS link so that we can visualize geochemical data in real time. So what is Leapfrog Geo? Leapfrog Geo is a workflow-based 3D implicit geological modeling tool which allows you to quickly construct models directly from various sources, including drill holes, points, and surfaces. Leapfrog uses volumetric algorithm called FastRBF to construct first pass surfaces quickly. The RBF, or radial basis function, is a mathematical backbone of Leapfrog. The surfaces, such as in here in the 3D scene, created can be modified and needed to fit your geological interpretations. So due to its implicit nature, your models can be dynamically updated to honor new input data at any time. This new data can be new drilling information, new surface information, or any useful inputs. Under the Geochemistry folder is the ioGAS link. We're going to use this tool to bring assay data from Leapfrog Geo as points or interval file to ioGAS, where you can interrogate, visualize, and classify data, then back to Leapfrog Geo where you can visualize and model the data. I'm now handing over to Putra, who will explain more about ioGAS. Putra?
Thank you, Alan, and thanks for the introduction. So for those of you who have not heard or used the ioGAS software before, I just want to give a brief introduction of what ioGAS is and why we do what we do here. So ioGAS is developed by IMDEX, a mining tech company specializing in development of cloud-connected devices and drilling optimization products to improve the process of identifying and extracting minerals for resource companies. And as a program, ioGAS has been around for more than 10 years now. It's a software that lets you interpret your geoscientific data. We have years of experience applying high-level advanced data analysis techniques to practical applications in interpreting your geochemical and other geological data, such as downhole gamma measurements and structural logging. So what we do best in ioGAS is in applying exploratory data analysis techniques to your geochemical data. And that is our focus through our very visual workflow. And that workflow in itself is suitable for looking at other data types as well. So it's not just for your geochemistry data. So you can use the workflow that we have in the program to interrogate spectral data such as those from OSIRIS and structural data such as the ones that we get from our IQLogger tool, and also our downhole gamma data from our UZ gamma tool as well. So that's ioGAS. So if you move over to the next slide, please, Ellen. Thank you. So this is an example of a typical workflow window for ioGAS. So this is an example of someone who wants to know more about the geological context behind his geochemical data. So say if you got your assay data from the lab that corresponds to the rocks that you have logged from the field, and you just want to know more about them, about the context, about their background, and what processes can be inferred from this. So you can see on the right-hand side of this window is a couple of classification diagrams. So this is what we call XY or ternary scatter plots with overlays of shape and lines, so polygons and polylines that allow someone to classify their data points. And it's a way for geologists to link back their geochem data to certain geological classification based on known composition, and also infer certain geological processes. So it's a process reduction technique. So it's a way for someone to visualize their geochemical data in a 2D or 3D space, and allowing them to link it back to what they know about the rocks, either from visual logging or from other ways that they have interpreted their data. And next to it in the middle, we have our decision tree. So that's what we call our classification and regression tree algorithm. So this is a way for someone to figure out which elements contribute the most to classifying the data points based on their geology and what they have logged in the field and things like that. And next to it, just on the left, is a wavelet plot. So, and that is a way for someone to define their boundaries using downhole data from either their instrumentation, from gamma data, or their geochemistry data that they plotted up on a downhole plot, such as this one. So it's allowing them to automatically pick up boundaries and enabling them to make better decisions on where your boundaries are sitting with respect to alteration or lithological processes. And just on the very left is a couple of principal components analysis plots. So in the bottom is an example of a biplot. So you're plotting up the result of principal components analysis on your data points, and you're plotting up the principal components axis on top of it. And you're just basically seeing which elements contribute the most to the variation that's represented by the data points. And you're basically linking all these processes that you're able to identify using classification diagrams and with some mathematical analysis as well to back that up. So we will go through some of this in more detail, especially on the right-hand side of the screen with the classification diagrams. We'll go through this workflow in more detail within this webinar. So thanks, Alan.
Thank you, Putra, for a brief introduction on ioGAS. I'm now going to show you some information about the data set that we're going to use. So there are 11 drill holes in this project. So displayed on the 3D scene are the different rock types. We've got 2 felsic rocks, A and B, and we've got a mafic rock, which is the dark blue in color. We have a total of 1,084 data points with 59 assays per suite per interval, and displayed on the right side of the screen are tables for your color, for assay, and also for your geology. The assay data is composed of major, immobile, rare earth elements, precious, and base metals. These assay groups can be viewed in ioGAS. Once again, I'll hand over to Putra, who will briefly discuss the Leapfrog Geo and ioGAS workflows. Off to you, Putra.
Thanks, Alan. So just jumping off on this slide a bit. So this is a display of how you would select your elements in ioGAS, and what we provide to our users is a way of easily selecting from a list of provided elements based on common groupings. So major elements, immobiles, and rare earth elements, they're grouped in a certain way that we can pick them easily from ioGAS, and we also provide a list of Pathfinder elements for common deposit types and that sort of thing. So this is just a way for you to group your elements together before you visualize them within ioGAS. So next slide, please. So I'm just going to go through the workflow that we're going to be presenting to you today. So the first workflow is igneous rock classification. So this is what we will do to look at your geochem data in ioGAS. So we're going to bring intervals data containing assay information from Leapfrog Geo into ioGAS, and we are going to use a combination of classification diagrams in ioGAS to classify the rocks based on certain processes and what we think are actually happening behind the data on its own. So, and what we ended up actually discovering from this is we were able to subdivide our log classification. So not just felsic A, felsic B, and mafic. We were able to actually split them up into subgroups just using a combination of relatively simple geochemical classification diagrams. And what we're able to do in ioGAS is we're able to save them as a new column, and we're able to push that across back to Leapfrog Geo, where Alan is able to turn them into a refined geological model based on our geochemical classification. So that's what we call the backflagging process. And moving on to the second workflow. So we were able to take this one step further, and we will again use a combination of simple classification diagrams, and in this case, a combination of the alteration box plot and a couple of molar element ratio diagrams to identify the processes really that that we can observe here in this rock. So it's important for us to go through the process of first identifying the lithology before we delve into the alteration. But the way that we've used this alteration modeling is we were able to identify the data points that corresponds to the processes that we were able to see using these diagrams. And then through the creation of new color groups based on this information, that's in a new column in ioGAS that we were able to backflag into Leapfrog Geo as a way for someone like Alan to create a new alteration model based on the alteration modeling that we've come up with in ioGAS. So that's the essence of today's webinar, and I'll hand over the control to Alan, who will go through the process starting from the Leapfrog Geo side of it. Thanks, Alan.
Thank you, Putra. So let's now jump into the live demo on Leapfrog Geo and ioGAS. I've now opened Leapfrog Geo together with a lithological model that we have previously created. It's a very simple model. It contains 3 lithologies, felsic A, felsic B, and the mafic rock. Again, for those who are not too familiar with Leapfrog, just as a brief rundown on the user interface, we have in here the project tree on the left side of the screen, which is designed with a top-down approach. The first half of the folder, so from topography down to around like meshes folder. So this is where data is imported or created. And the second half is where all the various models are going to be constructed. So from the geological models folder down to the block models folder. And of course, you've got in here the saved scenes and movies, sections and contours for presentation purposes. And lastly, we have in here a folder for geochemical analysis, of course. And you also have in here an option to import color gradients. We also have in here the 3D scene in the middle where you can interact objects, where as you can drag and drop things from the project tree to the 3D scene, and everything that is displayed on the 3D scene is actually listed down in here under the shape list at the bottom of the 3D scene. We can choose the different visualization settings, such as turning on and off layers, turning on and off objects, or determining what you want to visualize in the 3D scene. So underneath the Save Scenes folder, I'm just going to expand this particular folder over here. I've created a few save scenes which act as bookmarks. I'll be running through this for the purposes of this presentation. This is a great way of preserving perspectives of different objects, or to tell a story without bringing different objects into the scene. So one of the more important features mentioned earlier is that Leapfrog Geo is dynamic in nature. So any changes that you make to the data will automatically be reflected throughout. So I'm just going to go through with the following save scenes now. So these are the colors of the drill holes. And I'm just going to display the assay now with scandium and also titanium. So I've just set in here two examples by displaying scandium and titanium. However, under the drop down in here under the assay table, feel free to, you can choose whatever elements you want to display. For example, nickel. Right, so just gonna go through with the geology again. So these are displaying the three major lithologies, felsic A, felsic B, and the mafic rock. The first thing that we're going to do is we're going to construct a surface in between felsic A and B. So I've created an intrusion surface in here to model between the two lithologies. And after that, I was able to model the mafic rock as a vein. And then from there, I was able to create the simple lithological model. So everything happens under the geological models folder. I'm just going to expand this a bit more, and all the surfaces are created under the surface chronology by right-clicking on it. And then by creating the output volumes, of course, for those who are familiar, just double-click on the surface chronology. We activate the surfaces, click OK, and we create the output volumes down in here. Okay, let's move on. I'm just going to cut a slice through this simple geological model here. So just to give us an idea on how this lithology looks like at various sections. Okay, so the next step for us to do is I'm just going to connect now to ioGAS. So more importantly is you need to have a licensed ioGAS software. So I'm just gonna make this, just gonna collapse those folders. And first thing is, okay, if we start in here, if you see this ioGAS not connected, what you need to do now is to connect. All right, and make sure that you have ioGAS software turned on as well. And the next step that you need to do is to right click and then click on the new ioGAS data. So I'm now going to click on this option. And of course, you need to select the base table. In this case, I wanted to select the assay base table. And under the available column in here, I could choose all my multi-element data in one go and put them onto the other side under the selected columns, and then click OK. I'm just going to click cancel now because I've already created one in here. I'm just going to expand the ioGAS link. And this is now the ioGAS data. So I'm now going to hand over to Putra to open the link in ioGAS in order for him to interrogate the various multi-element assays that's available.
Thank you, Alan. So let me just bring up my screen. So just jumping off from where we left off with Alan. So we already brought the data into Leapfrog Geo, and then we've already made the geology model. And now what we want to do is we want to see if we can use ioGAS to refine your geology model, or even come up with a brand new geology model based on any classification that you made based on your assay data. So the next thing that we're going to do is, on my end, I'm just going to make sure that the link is turned on. And once that's done on the Leapfrog Geo end, in ioGAS, it's always a good idea to make sure that there's nothing open within the current workspace within ioGAS. So just leave it as empty as when you first start the program. So the link is already active within both programs at this stage. And before we go forward, I'm just going to show you a few things about the interface. So what we have at the top is a collection of ribbon tabs. So this corresponds to pretty basic functionalities split into each of these tabs. And most people will just live within the home tab for their basic graphing needs. And what we're going to go through now is the process of actually bringing in this new ioGAS data that you generated in Leapfrog Geo into ioGAS itself. So if we go into the File tab, and if we click on the Open Link menu, and before we do that, I'm just gonna try and make this a bit smaller so we can see both programs at the same time. So clicking on this icon, this will allow me to essentially bring in the assay data from Leapfrog Geo to ioGAS. So on the view here, we see the geology model. So we just like to turn all of this off for now. And we just want to check that we are looking at the same thing within ioGAS. So notice that everything is black here as I drag this new ioGAS data into the Leapfrog view. And that's because in ioGAS, when you first open a file, your color, shape, and size properties, so that's how your data points are displayed within any plot in ioGAS. They're displayed as black circles as default. So that's an important thing to know at the start. And what we can do now is we just want to make sure that our data has been aliased. So aliasing is a very important concept in ioGAS. So aliasing is a way for ioGAS to know that you're dealing with geochemical data in your file as opposed to purely numerical information. So it's a way for ioGAS to know that you're bringing in SiO2 in percent as an assay data, as opposed to SiO2_% just as a numeric information. And while it's simple enough to describe it like that, but it's important in a way that it allows people to plot their data in classification diagrams and do automatic conversion in the background. So say, if they want to create a molar element ratio diagram, if you have tried doing that in a place like Excel or things like that, it's quite a cumbersome process, especially if your data is all in silica in weight percent, for example, not in molar equivalent. So it's just one of those things that we'll need to check to make sure that all of your assay data has been aliased. So we're pretty happy with this because we've already done this step before. And what we want to do now is we want to select a few elements. So say if we start looking at your immobile elements, because we know that we're dealing with a number of volcanic rocks in this area. So what we want to do is we want to use a combination of these elements to see if there's any pattern in them that can be used to further differentiate them apart. So the best way to do that is to select them as I did just then, and then open up a scatterplot matrix. And that allows you to see that there might be some subpopulation within this data that we can cluster up and easily identify using our attribute manager and things like that. So the most powerful thing about ioGAS that I find really useful, and the visual aspect of it is absolutely essential for someone examining their data visually, and it's the way that we can assign a color group to a selection of data points and have that be reflected in every other open plot in ioGAS. And that allows you to see that this cluster right here, and then if I create a new one, if I use that to attribute just this cluster, just manually by eye, and you can see how it corresponds to clusters in every other related elements. And it's one thing that sort of got you thinking, what processes am I actually looking at here? So this is an important step. The first time that you're trying to do this sort of thing in ioGAS is that we provide a number of advanced analytics tools and diagrams and geochemical classification within ioGAS. But it's important to know that if you know what elements are useful in splitting out between certain volcanic rock types, it's a pretty good idea to just plot them up in a simple scatter plot matrix like this and attribute them and see where they plot in 3D space. Because what you can see here, once you get them plotted up in Leapfrog Geo, you can see that there's actually two layerings here. So based on the two clusters that I've identified just by visual identification, you see that they correspond to stratigraphic level. And so this is a concept that we will explore in a bit more detail now. So just going to clear out all of the color groups here because we're going to do something else. So I'm just going to minimize this, and I'm going to open a classification diagram. So as I was saying earlier on in the presentation, a classification diagram is a way for someone to link their geochemical data back to a known geological process or geological classification based on a similar rock type. So most of these diagrams are based on the literature. So if you're looking at sort of the same rock that the author or the maker of the paper or the source of this diagram that they used to make those diagrams in the first place, if you're looking at the same sort of rocks, then it's a good idea to start using these diagrams. But it's absolutely important to know that when you're looking at these diagrams, to know exactly what you're looking for. So what's important to look at from this one, for example, this is a task classification diagram. So it's using a ratio of your sodium plus potassium over silica. And you can see that the rock types are actually just pretty uniform all along the y-axis, but the SiO2 is the one that's splitting up the felsic and the mafics in a way. And that's how you would use this sort of diagram to classify your data points. And the cool thing about this sort of classification diagram in ioGAS is that it's divided into sub-classification fields. And classification fields, the fact that you have data points plotted on top of them, means that the obvious next thing to do is see where a data point is plotting, and you color them based on where they plot in this diagram. So if I click on this small button here, color rows by polygon, you can watch as how it auto attributes based on where they plot within these classification fields. And you just see it ticking away in the background or on the Leapfrog side on the right-hand side of the screen. And you can see how it updates automatically. I see this layering right here, right on the Leapfrog Geo side. And that is exactly what we expect to see. So what we've managed to find is that we're able to split the rock types based on where they plot within this diagram, and more specifically based on the SiO2 value. But we can go one step further, and if we think of these rocks as being slightly altered, so we don't know much about these rocks, right? And this is the sort of thing that you would get if you have limited logging and you don't know much about the rocks in the first place, or you're uncertain about what they are. But you know for sure that there's a bit of alteration here, which might move some of these numbers around, especially on the y-axis, not so much on the x-axis, but with your sodium and potassium. You know, if you expose them to a bit of alteration and weathering, you would move some of these numbers around. So you would want something that's a bit more robust in that sense. So we provide a diagram for looking at immobile elements in this instance. So a particularly useful one that you would use in that scenario is plotting niobium, yttrium versus zirconium over titanium in the Pierce 1996 diagram. So this is absolutely useful because you're looking at elements that are known to be relatively immobile in weathered or hydrothermally altered settings. So what we can do now in here, so we've identified our rock types based on a task diagram, and we'd like to subdivide the dacite field even further, because as we can see here, the green rocks that I labeled as dacite from the first diagram, you see that they are present in two fields within the rhyolite dacite and the andesite, basaltic andesite. So what we can see is actually some of the dacite were probably mislogged as dacite in this classification. So they're probably andesite, basaltic andesite. So what we can do is we can turn everything off except for the dacite, and then we'll just create a new classification for andesite, basaltic andesite, and I'll just call them ABA. And what I'll do now is I will reclassify the samples that plots here into a new group. So I got them active in the attribute manager in ioGAS. So before I move on, so attribute manager is basically, as you've seen in the last 5 minutes or so, attribute manager is where the visual heart of ioGAS is. So everything you do here is reflected in every visual aspect of ioGAS. So every other open plot and every other diagram and things like that. So I'm going to make sure that ABA is active, and I am going to attribute this into its new group. And this is what we call the new ABA group, and we just see where everything sort of sits. So what we came up here is just a way for re-logging our classification based on where they plot in these two relatively simple diagrams. And it's important to know the processes that's tied to these diagrams and what works with your data. First of all, what minerals gets dissolved within certain analytical method, and whether it's appropriate to use this diagram or another diagram. But so far, what we've seen here sort of works in a way that it subdivides them into stratigraphy that we can easily model in Leapfrog Geo. And before we move on, let's just very quickly see if we can change the shape of this to the major lithologies, so felsic A, felsic B, and mafic. And we'll just see what happens if I turn things on and off. So if I turn everything off, and we'll just see where the felsic A rock sort of sits. And you can see that I've divided felsic A into several groups. As it turns out, these guys right here, they're not felsic A at all. They're actually more correctly classified as basaltic in composition. And it's the same thing with the other one. So it's a way, it's not asking you to replace what you know. It's just a way for you to sort of think back about your rocks a bit more and trying to see if you can improve them further by combining your log visual inspection of your rocks with your geochemical data. And as such, it's always a good idea to get really good whole rock geochem data, because that allows you to do this sort of thing. So the next thing that I'm going to do is, and I've already done this step before, but basically what you can do now is, if you go to the data tab in ioGAS, you're able to create a new variable from color. So you're basically creating a new column based on this color attribute, and it will be shown. So I'm just going to create a new column in colors. I'm just going to click cancel because I've already done this. And so if I just pretend I've already done that, and if you go to the right, click under task classification, so right at the end. So I've already reclassified them into a new into this new column based on the classification that I did just then using the color groups. And basically that process in itself, the newly created column, is actually pushed back to Leapfrog Geo as a new backflag column under assay, and it's called color TAS class. And this is what Alan is going to use to refine his geological model, to make a new geological model based on this classification. So over to you now, Alan. Thank you.
Thank you, Putra. I'm just going to share my screen again. Right, so as Putra discussed, this is now the backflagged alteration assemblage using the task classification diagram, and everything is backflagged from the drill hole data down to the assay table. If you're gonna look in here, that's now the column that was added in Leapfrog Geo from ioGAS. Okay, I'm going to go through the save scenes and movies again, just to continue on with the discussion. And also, Putra earlier on was able to classify the day site bodies into two. So we've got in here, he's classified the day site. This one here, the dark blue one remains as day site, while the other one has been classified as ABI, or the andesitic basaltic andesites species, rock species. All right, so moving on to the task classification again, and then we're now able to model this as intrusion surfaces. So I've got the basaltic andesite and dacite modeled as intrusion surfaces, and next is I was able to model my basaltic contacts, rhyolite and andesite as deposit surfaces in Leapfrog Geo. So everything in here, if I go up, go down to geological models folder, everything will be constructed again under the surface chronology. So these are the surfaces that are actually being shown on the 3D scene now. All right. And then from there, I've generated my output volumes. And this is now the output volume that was created, and based from the predictions that was shown in ioGAS earlier on, clearly reflects the layered nature of the different rock types that was modeled into Leapfrog Geo. So if we're gonna compare this with the simple lithology that was modeled earlier, which you can see is just three lithologies to start off with, and through ioGAS we're able to classify this further into various rock types. All right, I'm just going to change over the screen now back to Putra in order to explain more about alteration modeling. After you, Putra. You can share
Fantastic.
your screen.
Thanks, Alan. I think you're still presenting.
Yeah, hang on a second.
That's right. Thank you.
Yep.
Got it. So we're just gonna touch on a few things that we did just before. So we've successfully created a new geology model based on your combination of TAS and TRS 1996 classification in ioGAS, and we've allowed ourselves to subclassify our known geology into new subgroups. And so this is a way for you to refine your lithology model. But another thing that you can do with the data that you have here, and this is also dependent on how comfortable you are with the alteration that you're looking at and the processes that you would sort of expect. But what we are able to do now is we're going to do some alteration modeling. So what's a good place to start for this? So I'm just going to maybe turn everything off as a start in Leapfrog Geo, and I'm just going to look at the assay data on its own. And I'm going to reset the shapes to default, and I'm going to turn off the color groups as well. So we're just basically going to start from scratch. We've already backflagged this as a new information column in ioGAS, so you can always go back to it without any fear of having to repeat the process again. So it's already saved as a categorical column in ioGAS, so you can always go back to it. So we already have the information present somewhere. So what we can do now is I'm going to open an alteration box plot. So this sort of diagram, as you can see here, it consists of two axes. So the alteration index, Ishikawa alteration index, versus the chloride carbonate pyrite index, or CCPI. So the alteration box plot was developed specifically for the study of alteration associated with VHMS systems. And even though it's used for that purpose, and while we're not certain that we are looking at a VMS deposit here, we can use the processes that's represented in this sort of diagram as a starting point. So by no means we should take the information that's present in this as gospel, or as a silver bullet to let you know if you're looking at this sort of alteration type. But it's a good place to start. And why is it a good place to start? And it's because in this diagram, which consists of the AI and CCPI axis, so the x-axis represent uh, a loss of sodium and calcium and gain of potassium and magnesium within this index. So that's represented by the development of muscovite and chloride from alteration of sodic plagioclase. And the y-axis, CCPI, is constructed in a way that it represents an increase of magnesium and FeO related to chloride development. So it allows you to separate out between muscovite and chloride development. And if you're aware of that sort of processes and the fact that we label the nodes that corresponds to development of this mineral, so you can see on the right here you have IL for illite, and you have here AB for albite, and CHL at the top for chloride. So as long as you're aware that this diagram represents the development of that assemblage of minerals, and you're familiar and comfortable with that process, you're able to use this sort of diagram to start thinking about how you can model alteration in your data. And the reason why I do this is because it's a quick and easy way of coloring your data points automatically based on where they plot here. So we managed to find great success in coloring where the data points plot within the polygons here, because the data points that plots within 3 boxes in the middle, they represent more fresh sort of composition. So, and by fresh, I mean, less altered than the ones that's outside of the box. And we can go one step further. And if we can assume that there's little albite development or epidote sort of mineralization in these rocks, and basically what we can do is we can expand the field for the least altered rocks a bit more to the left-hand side. And then we're going to do the same thing with the middle box as well. So we just color them up as dayside. So basically what we're doing is we're just expanding the least altered classified rocks into a bigger classification, because we're comfortable in knowing that the rocks that plots here, that they don't represent any sort of alteration, even though they plot outside the least altered boxes. But we can call these guys some form of hydrothermal alteration. And one thing to be really careful about in this is that there's a certain risk in looking at this diagram on its own, because samples that plot higher up on the CCPI axis, for example, because you're looking at a ratio of magnesium plus iron over these elements, and because you're looking at some mafic rocks in here. So if you remember, just in the first workflow, we've actually identified that some of these rocks actually correspond to a basaltic composition. And what it means is that while it's plotting up in a hydrothermally altered field, they may not represent hydrothermal alteration. They just represent a more mafic variant in your data points. So samples that are actually represent more mafic composition with the higher FeO and magnesium amount. So so what's the takeaway here? The takeaway is that we recommend using this sort of diagram in conjunction with molar element ratio diagrams to identify processes more closely. So what I'm going to do now is I'm going to just keep this open here, and I'm going to open a general element ratio diagram. So I'm going to start with this ratio of sodium over aluminium versus potassium over aluminium. So if you're not familiar with molar element ratio diagrams, basically, if you remember the stoichiometric composition of muscovite and all your feldspar minerals, you know that this sort of diagram represents that ratio of, say, sodium over aluminium in albite, and then a ratio of, say, potassium to aluminium in muscovite, which is 0.33. So you're using the stoichiometric composition to define where the nodes, this dots sort of sit in this sort of diagram, and you're able to use this in conjunction with our known composition in ioGAS. So what we provide within ioGAS is a way to plot, say, known composition of sheet silicate stoichiometric composition. So you have an option of selecting from chloride and muscovite and all of your clay minerals composition here that would be familiar to you in this sort of alteration setting. So if we just turn everything on here, and then seeing where they plot in this sort of diagram, and you can see that the muscovite node sort of sits here and elite here. So this is a way for you to basically see the processes that you would expect to see in this sort of rock. So it's overlapping here, but you have a bunch of chloride composition that sits here. So what can we tell basically from this diagram? Basically, we're seeing how we can further subdivide the rocks that were logged as hydrothermal into a way that's more, that's more easier to understand and more useful to us. And the way we've done that is we've created new color groups based on where they plot. So I'm just going to show you a very quick example before we move on. So I'm going to basically set everything to invisible except for the hydrothermal altered rocks. And then I'm going to create a new color group. And I'm just going to create a new color group for intense muscovitization. And I'm going to label the rocks that are here as a new color group. And I'm going to create a new color group for prioritization. So this is a way for you to basically subdefine your classification a bit more, right? And so I've done this process a bit manually before, so I'm just going to jump through. I'm just going to cheat a bit, and I'm going to auto attribute by what I've done. And so basically, I've done this process over the entire data set just before this webinar. But basically, this is a shortcut that I did because I've already done this. So the process involved was knowing that you're looking at a range of alteration from a sodic plagioclase to a more, so that your sodic plagioclase composition will plot somewhere here, and then you would see a pattern that leads them to be more altered towards here, and you see development of chloride here, and you see sort of like the in-between zone, so with the slight muscovite alteration as opposed to intense muscovitization, and slight colorization, sort of like that halfway point between more fresh composition and this one. And it's important to know exactly what processes that you're looking at, because as I've tried to do here is I have managed to redefine the alteration process for the least altered ones. And you can see that the least altered rocks that are identified in the alteration box plot, that when you bring them up, that they actually belong in 3 boxes, and that's why they're resulting in 3 color groups. So and because of that, they're represented in a varying CCPI amount because of that mafic to felsic gradient, and it's also represented to some extent in the x-axis here. So it's important to know the processes that you're looking at, and And by applying large-scale sort of alteration modeling to this based on mineralogy of what you're expecting to see, and then plotting them up as color groups within ioGAS, and then subdividing it as such based on the minerals that you would expect to see, and then just doing the same as before. So just creating a new color group based on this. So, and I didn't show this in the first workflow, but I'm just going to do it now. So I'm going to create a new color group, and that's going to be created as a new text column within ioGAS. And then within Leapfrog Geo, it's going to be reflected under the Assay tab once that's done. And basically, that allows you to create alteration model within Leapfrog Geo. And just one thing before we proceed. So just while on that subject of the alteration box plot, the total FV alteration box plot, you see that your least altered rocks are plotting in the 3 boxes in the middle. And this is why it's important to know that you will need to always look at this not just on their own. So you'll need to know why they're different on the y-axis. And if you plot up your CCPI versus your SiO2 value, what's actually interesting is that it varies with the silica that you're looking at here. So it's important to know that the variation in your CCPI is actually controlled not just from the value of the numerator and denominator of the index, but also by other elements that might affect it as well. And looking at this in conjunction with your log lithology, or for example by the task classification, you're able to sort of see what's actually happening here. So you can change the shape to the task classification that we did in workflow 1, and you plot them with the alteration modeling, and you basically allow yourself to infer certain processes based on what you've already done so far. So it's important not to just look at these diagrams on their own or these plots on their own, but using the various tools that we have in ioGAS, looking at them in conjunction with one another to reach a certain conclusion, and that is the alteration modeling that we came up with. And as that's already being backflagged into Leapfrog Geo as a new column under the assay table here, Alan can create a new geology model based on this new backflag information. So over to you, Alan. Thank you.
Thank you, Putra. Just gonna change over to my screen. Right, so back to Leapfrog Geo. This is where you can find the backflag alteration modeling in Leapfrog Geo. So I'm just gonna highlight, just click on the edit colors menu in here. This is where you can see the clartization occurs, intense muscovite alteration, and these are your least altered alteration. You've got light chloride alteration in here, and you also have the muscovite alteration. Just gonna click OK. Gonna go through back to my save scenes. First is, in order to model this, because the nature of the alteration is a bit layered, a bit complex as well. And what we need to do is, I did a bit of a simplification to the alteration. So what I've done is I've grouped those least altered, it became fresh, and then from fresh to intense muscovite alteration as well is one group. The chloride alteration is one group, as well as the moderate muscovite alteration is also one group. So just going to show you this. This is now the model, the fresh to intense muscovite alteration. Secondly, I have the moderately muscovite alteration at the base of the fresh to intense muscovite alteration. And lastly, what you have in here is your chloride alteration. Generating the output volumes, we now have the fresh in the background as well. So again, due to the layering nature of both of the rocks and alteration. You can see in here the alteration output volumes that was produced is also layered. Want to slice through on the alteration model now, just to gain a bit of an appreciation on how this looks like at various sections. Okay, so just want to summarize. So again, just to summarize this, we've generated the simple lithology first, which is displayed on the 3D scene. And then we made a detailed rock classification on the simple lithology. And then lastly, we generated an alteration model out of that. So just going to show my last slide. So Leapfrog Geo is a workflow-based 3D implicit geological modeling tool, which allows you to quickly construct models directly from various sources, including drill holes, points, and surfaces. So ioGAS is an exploratory data analysis software for the detection of patterns, anomalies, and relationships in your geochemical data. We can bring data from Leapfrog Geo to ioGAS, and then back to Leapfrog Geo through the ioGAS link in the form of points or interval data. And then lastly, rock alteration or mineralization classification can be established in ioGAS and viewed and modeled in Leapfrog Geo. Thank you so much for your time. Do you have any questions at this stage? So we'll allow a few minutes for questions.
Hi, Alan and Putra. Great presentation. It was fantastic to see the workflows from Leapfrog to ioGAS and back to Leapfrog again. We do have a couple of questions from attendees online. The first question is for Putra. How can ioGAS predict the type of mineralization within the data set?
So ultimately, that depends on what you're trying to achieve within ioGAS. So if you, and it also depends on what data that you have. So if you're looking at purely geochemical data with some information about what interval corresponds to what sort of mineralization, you're sort of halfway there in terms of determining what mineralization is present within your data. So generally, it's a very GIS type approach in that the more you know, like the more you can make a certain about the more you can be certain about the interpretation that you come up with. But also in terms of what we can do in ioGAS is our classification diagrams will allow you to see if you're within the ballpark of a certain prospective rock type. So one of the diagrams that we came up with quite recently is a Scott Haley diagram, just using a ratio of a couple of immobile elements in porphyry exploration. So that's looking at a ratio of vanadium over scandium versus scandium, and that's a really good way of determining if your data is situated within prospective porphyry copper field. So that's just one example. And as I was showing in the presentation, we have a library of mineral composition and composition of known deposits, famous deposits. So those are the ones that Carl Brohart has collated in his OSNACA dataset, which we have implemented into ioGAS as a library. So it's a library of known composition of type deposits, so famous deposits within certain deposit types. So say if you, for example, you're exploring for IOCG type deposit and you have a sample that you think would be within the ballpark of say an Olympic type deposit, and you can sort of check if your data is plotting within that ballpark, within that range. So that's one way of looking at it. But as always, it's always a good idea to have more info. So you plot your geochemical data in diagrams in ioGAS, and you display other information such as rock type and that sort of thing. And if we have time, I might be able to share my screen and just show a few other things. But we'll leave it up to another couple of questions before doing that, if that's all right.
Thanks, Putra. Great answer. This next question is for Alan. So can I use point data such as my surface samples in the same workflow that you just presented today?
Thank you so much for the question. Very interesting question. So yes, you can. So if you have surface samples with multi-element geochemistry, similar to what we have in the drill hole, so you can use this. Actually, I've dealt with a previous project from one of our clients, and they've got soil samples and with the multi-element geochemistry, and we were able to determine prospective areas through that particular data. That's all.
Thanks, Alan. Next question is for Putra. Is there a recommendation you have for the number of elements required for a workflow like this? Do we need 33 as in the example that you used today?
So look, in terms of elements, it's really not how much elements you have analyzed, even though that could be nice, but it's also how they're analyzed and with the certain analytical methods that's required to get the best out of your data. So I guess the answer to that is pretty broad, but having a full list of 33 elements and having high quality lists of 20 something elements versus 60 element data set that's analyzed using the lowest cost analytical method, it might be better to go with ones that are more high quality. And I think it's always good to emphasize that it's preferable to know what you're trying to look for. So what alteration assemblage, what lithology, and what phase of alteration or lithology that you're expecting in your data, and that sort of determines how many elements you need, what elements you need to look out for, and the quality that you want to seek in your data, because ultimately that will determine what sort of diagrams, classification diagrams, and what sort of advanced analytics tools that you can use in ioGAS. And of course, if you're dealing with historical data set as well, you have to bear in mind the sort of elements that will be advantageous to to complement your historical data set if you're not re-assaying them, for instance. So just that sort of thing that will be need to keep in mind. So that's a long-winded answer to your question. But the short answer is 33 elements. As long as they're of good quality, then yeah, you can go far with that, or even less, especially if they're of high quality and they're useful for the sort of thing you're looking for.
Awesome, thanks, Putra. I have another question here. What do you find are the most effective alteration tools when working with meta sediments? So if you have things like detrital silicates, the question's for Putra.
Oh yeah, thanks. So when you're looking at detrital silicates, we don't have a particular diagram that will be quite useful for that, even though we have a bit of sort of like some more weathering trend sort of alteration diagram. So if you're familiar with the ACNK sort of diagram, they may be useful for what you're trying to achieve, but ultimately I think if you're working with meta sediments and looking at which include detrital silicates, you probably will do well with just plotting them up in a few scatter plots in ioGAS and using a combination of weathering trend alteration diagrams within ioGAS, so within that folder, and just exploring what sort of works with your data and seeing if things are plotting where you expect them to be.
Awesome, thanks, Putra. We have one more question, and then for the rest of the questions, we'll follow up with you individually to answer them. So this is a question based on your experience for both Alan and Putra, but if you have different classifications based on lithology and geochemistry, like we saw a little bit in today's workflow, what are your best options for evaluating which classification has more confidence?
So I can start with this one, Alan. So I guess based on experience, just if you're looking at just purely geochemical data, and if you're trying to reconcile between what one diagram says and what your log geology says, it's always a good idea to step outside the circle and sort of think outside the box on what sort of other data that you can put in. And even though it doesn't directly answer your question, but it's always a good idea to add things like spectral data, so from Osiris, for example, and if you use that in conjunction with the workflow that we presented here today to be more certain of what you're looking for, because ultimately, what we presented here today, so for example, with the sodium over aluminium versus potassium over aluminium molar element ratio diagram, it's not a silver bullet to sort of indicate the sort of alteration that you would see. So for example, in this data set, there's no information in the file what sort of alteration is present, even though, if I can just quickly share my screen, Alan.
Kath, you able to? Yep, thanks.
Yep. So it's just be very quick. So in ioGAS, we're able to basically display a label right next to each data point. And I'll show you this later after this webinar if anyone's interested in more detail. So basically, if I can show item labels, so each of the rock type here, each of the data point has been logged visually in the field. So what I've classified as chloratized rocks, and when you zoom into these data points a bit and you see how they're classified in the field, chloritic mafic flow, so that's what they're classified as, and chloride carbonate altered basalt, and chloride carbonate schist, and chloratized quartz porphyry. So it's this sort of thing where you're reconciling your log alteration with the alteration modeling that you've identified through this sort of diagrams. And if you move up a bit into the sericite alteration field, you see that it's quite consistent with what we've identified using our geochemical classification. So you got your sericite chloride quartz porphyry tuff, and sericite altered quartz porphyry again, and sericite quartz, and a few other samples that's classified as sericite altered. So if you want to be certain that you're looking at the same thing, it's always a good idea to first bring it back to your geology. So that's number one. And number two is you want to use a combination of not just one molar element ratio. So say you can also plot things up in a chloride molar element ratio diagram. So this is a way to separate out between your muscovite and chloride alteration, and you can see that in the tie line between muscovite and chloride, you have some samples that exhibit sort of that halfway point between chloride and muscovitic composition. And of course, you can update this classification, right? So this is an interesting one. So you have a couple of samples here that's classified as sericite chloride, quartz porphyry, and chloride carbonate sericite. That's sort of in a tie line between muscovite and chloride. And linking it back to log geology and using a combination of, not just one molar element ratio diagram, but using multiple molar element ratio diagrams, you're able to identify processes, and then you can refine your classification more, and then see them being reflected in Leapfrog Geo in real time, and update your alteration modeling in real time as well. So that's how you can reconcile sort of different classifications that exist. But it's always a good idea to not just use one diagram, just have to use multiple and use your best judgment. And ioGAS is easy to use it, in terms of applying color groups and that sort of thing, which means what you interpret is reflected visually in real time, instantaneously, in fact. So yeah.
Yeah, just adding to what Putra is saying, you need to have at least the 4 ingredients in order to make your best judgment. The 4 Gs are actually your GIS data, where it lies in 3D space. You need to consider also the logging, the mapping, and also the geochem data as well. If you've got multi-element and geochem data, SWIR data as well. In terms of geophysics, you need to have you need to combine it with magnetics, gravity, IP, EM. So aside from having robust geochemical data, you need to basically, in order to classify this more confidently, you need to combine this together with all the other ingredients such as geology, geophysics, and GIS data. That's all at this stage.
Thanks, Alan and Putra. Those are great responses. That's all the questions we have time for today. We'll follow up after the webinar with questions from the other users.
Right, so our next Technical Tuesday workshop is on the 25th of August. It's about Leapfrog Works contaminant solution. So two of our colleagues will be presenting this, so watch this space. And lastly, if you want to get in touch with the Sequent support team, please get in touch with us through support@sequent.com, or if you want to get in touch with the ioGAS team, if you want to learn more about ioGAS, you can get in touch with them through their global help desk, which is under reflex.com/product/ioGAS. Again, thank you so much for your time, and I hope to see you all soon again to our future webinars, Technical Tuesday webinars. Thank you so much.
Thanks, everyone.